Welcome to All in All. Today, we're embarking on an extraordinary deep dive. We're heading out into the solar system to the colossal gas giant that, well, really reigns supreme out there, Jupiter.
It really is the king, isn't it?
Absolutely. Imagine a world so immense it dwarfs all other planets combined. It's a celestial body that has profoundly shaped our cosmic neighborhood, maybe even influenced life right here on Earth.
That's right. And our mission today really is to pull back the layers of this fascinating planet. We're going to explore its mysterious origin, how it got started.
Yeah, and how it's changed its surprising evolution over billions of years.
And its profound significance, its impact on the whole solar system, and, even its practical relevance to us, to humanity's ongoing quest for knowledge.
Okay, so we'll explore how Jupiter came to be, how its very existence might have created our asteroid belt.
That's a big one. And the whole story behind its reputation as Earth's protector, is it really that simple?
We'll look into that. And what studying its crazy stormy atmosphere and those icy moons tells us about the universe and maybe our place in it.
Yeah, get ready to uncover some truly mind-boggling facts, maybe shift your perspective on this giant we think we know.
Okay, let's unpack this from the very beginning then. Jupiter's genesis. How did this colossal giant actually come into being? The foundation, I guess, for understanding any planet's formation is that widely accepted solar nebular disk model.
That's the starting point, absolutely. This model suggests that our solar system, and probably most others, formed from just this massive rotating cloud of gas and dust, a nebula.
Wow.
And over millions of years, this cloud gradually collapsed under its own gravity, flattened out into a disk, and started spinning faster, like a figure skater pulling their arms in. The central part, that became our sun, and the material left swirling around in the disk, well, that's what eventually clumped together to form the planets.
It's quite an elegant picture.
It is. It was first really put forth by Immanuel Kant way back, and then refined by Laplace. It's really the bedrock of modern planetary science.
And what makes it so compelling? Like, what's the evidence that points to this disk idea?
Well, it explains several key things we see today really neatly. Think about it. All the major planets, they orbit the sun in roughly the same plane, almost flat, right?
Yeah, like they're on a cosmic racetrack.
Exactly. And they all orbit in the same direction, which also happens to be the same direction the sun itself rotates. These common features, they're strong indicators that everything formed from this single rotating flattened disk of stuff.
Okay.
Now, when we talk about the formation of gas giants specifically, like Jupiter, the process gets a lot more complex than for rocky planets like Earth. And scientists are really looking at two main competing models right now.
Two main ways a giant could form.
Yeah, basically. You've got the core accretion model and then the disk instability model. Both offer, pretty distinct pathways to building such a massive world.
So let's dive into the first one. Core accretion. How does that work for something as huge as Jupiter? It sounds like it starts small.
It does, but then it really snowballs, you could say. In the core accretion model, it's a multi-stage process. Think of it like building a giant snowball in a cosmic blizzard.
Okay.
First, tiny dust particles in that protoplanetary disk, bits of rock and ice, essentially they start sticking together. Electrostatic forces, maybe sticky organic coatings, that sort of thing.
No.
These then gradually accrete or clump together into larger and larger solid bodies. Eventually you get planetesimals, small, rocky, or icy celestial bodies, maybe kilometers across.
Okay, building blocks.
Exactly. And over time, these planetesimals collide and merge, building up a solid core. Now, for a giant planet like Jupiter, this core needs to reach a critical mass, typically a few times the mass of Earth, maybe around 5 to 10 Earth masses. That's the initial, slow, kind of painstaking foundation phase.
And then once you've got that solid core sitting there, what happens next? Does it just keep gathering rocks, or does the gas come into play?
That's where things get really dramatic. Once that critical core mass is reached, its gravity becomes strong enough to start rapidly pulling in vast amounts of gas, primarily hydrogen and helium from the surrounding protoplanetary disk.
Right, the stuff the disk is mostly made of.
Precisely. And this leads to what we call runaway gas accretion. Imagine that snowball suddenly becoming like a superpowered vacuum cleaner just for gas.
Wow.
The gaseous envelope around the solid core grows exponentially faster than the core itself. It just balloons incredibly quickly.
And how long does that go on for? Does it just keep grabbing gas forever?
Not quite forever. This rapid accumulation continues until one of two things happens. Either the growing planet's immense gravity carves out a distinct gap in the disk around it.
Ah, like clearing its path.
Exactly, a process called tidal truncation that essentially starves the planet of any more gas from its immediate vicinity. Or the other possibility is that the solar nebula itself, the main source of the gas, simply dissipates over time. The young sun gets more active, its solar wind gets stronger, and it blows away the remaining gas.
So it's a race against time, then, to grab that gas before the disk disappears.
It absolutely is. That's one of the key challenges for the core accretion model, forming that core quickly enough before the gas is gone, which typically happens within a few million years.
Are there specific conditions in that early disk that make this core formation and then the runaway gas part more likely to happen?
Oh, definitely. The conditions in the protoplanetary disk are crucial. Core formation is thought to be more favorable in regions where there's a higher density of solid material, think dust and ice.
Makes sense. More building blocks.
Right. And perhaps a bit surprisingly, maybe in protoplanets with lower initial masses.
Lower masses, why is that?
Well, the thinking is they have longer contraction timescales. They don't heat up as quickly, which gives them more time to patiently accrete those planetesimals before the gas disk vanishes. Also, lower internal temperatures and maybe lower convective velocities within these early protoplanets could help support the formation of a stable, substantial, solid core.
Interesting. So what's the final core like in this model? Is it always the same size?
Not necessarily. The final predicted core mass can actually be highly variable. Models suggest it could range from practically zero if the gas accretion was super efficient early on to potentially hundreds of Earth masses, though that seems less likely now. And these cores are thought to be primarily composed of refractory materials.
Refractory meaning?
Meaning elements and compounds that can withstand high temperatures without vaporizing. Things like iron, nickel, silicates, rock-forming stuff, basically, and maybe some ices if it formed far enough out.
Okay, so that's core accretion, a gradual buildup, then a runaway gas phase. Yeah. But you mentioned another idea, the disk instability model. That sounds a bit more dramatic. How does that one work?
It certainly is more dramatic, yeah. The disk instability model proposes that giant planets can form much, much more rapidly, possibly in just thousands of years, not millions.
Wow, okay.
Instead of building a solid core first, this model suggests that certain regions within the protoplanetary disk itself, maybe due to density fluctuations or gravitational instabilities, simply become so massive and cold that they gravitationally collapse under their own weight. They fragment directly from the disk gas and dust to form a planet.
So just collapsing straight out of the disk.
Pretty much. Think of it less like building a snowball layer by layer and more like a dense part of a cloud collapsing directly into a very, very big gas droplet.
So this doesn't need a pre-existing solid core at all?
Strictly speaking, no solid core is needed for the initial collapse itself in the purest form of the model.
Is this model as widely accepted, or are there, hurdles or debates around it?
There are definitely ongoing debates and challenges. A primary one revolves around the critical cooling timescale. For one of these clumps of gas to actually collapse and remain stable enough to form a planet, it needs to be able to cool down very, very quickly.
Why quickly?
Because otherwise, the internal pressure from the heat generated during the collapse will push back and resist further collapse, potentially just causing the clump to dissipate again. So efficient cooling is key.
And that's hard to achieve.
It can be, depending on the disk's opacity and other factors. Also, the numerical simulations we rely on to model these incredibly complex processes face challenges. There are debates about how accurately they represent things like turbulence, or what we call artificial viscosity, basically, how sticky the simulated disk is, and also the level of detail, the spatial resolution. These technical details can actually significantly change whether or not clumps form and survive in the simulations.
Sounds tricky to model.
It is. Though, interestingly, some studies suggest that even if a planet starts forming via disk instability, planetesimals floating around could still get captured by this forming protoplanet. They might then settle towards the center over time, potentially building up a core mass within the gas giant after its initial formation, especially if the initial collapsing clump was already enriched with heavier elements.
So maybe a hybrid scenario.
Possibly. It's an active field of research. We're getting amazing observations now of young star systems, like the one around the star AB Orgy, which show these incredible spiral arms and bright clumps within the disk. These might be signs of planets forming via disk instability right now.
Fascinating. So whether it was through a slow buildup or a rapid collapse, Jupiter eventually came into being. But once this colossal planet formed, it didn't just quietly settle into orbit, did it? It became this dynamic force, literally reshaping the early solar system through its movements.
Absolutely not. It was likely a major player from the start.
And that brings us to one of the most intriguing and maybe still debated ideas in solar system dynamics, the Grand Tack hypothesis.
Ah, yes, the Grand Tack. It paints this remarkably dynamic picture of our early solar system, like a kind of planetary ballet or maybe more like planetary bumper cars that reshaped everything.
What's the core idea?
The core idea is that Jupiter is likely the oldest planet in our system. It probably formed incredibly early, maybe just a million years or so after the sun itself ignited. That's potentially a full 50 million years before Earth even finished forming.
Wow, really ancient. And where did it form initially?
It's believed to have initially formed at or perhaps just beyond what we call the snow line. This is a really crucial boundary in the protoplanetary disk. It's the distance from the young sun where it's cold enough for volatile compounds like water, methane, ammonia to condense into solid ice particles.
So having ice available helped it grow faster.
Exactly. More solid material available to build that initial core, if you follow the core accretion model. This snow line was probably around 3.5 astronomical units, or AU, from the sun back then. Remember, Earth is at 1 AU.
Okay, so 3.5 AU, but it's further out now, around 5.2 AU. So it moved.
Significantly, and this is where the Grand Tack really gets its name. The hypothesis suggests that Jupiter, once it reached a certain mass, didn't stay put. It actually migrated inward, quite dramatically.
Oh, inward, towards the sun.
Yes. Possibly all the way into about 1.5 AU from the sun. That's inside the current orbit of Mars.
Whoa. What would cause it to move inward like that?
It was likely driven by gravitational interactions with the dense gas disk that still surrounded the young sun at that time. This is a process called type 2 migration. As Jupiter grew massive and cleared a gap in the disk around itself, the gravitational forces from the gas piled up on the outer edge of the gap, and the drag from the gas inside the gap tended to pull it inward, causing it to spiral closer to the sun.
Okay, so it spiraled inwards to maybe 1.5 AU.
Right.
But it's not there now, so how did it get back out to 5.2 AU? That's the tack, right?
That's precisely the tack. The hypothesis suggests that Saturn, which was also forming around the same time, maybe a bit later and further out, was also migrating inward, possibly even faster than Jupiter for a time.
Okay.
Eventually, Saturn caught up to Jupiter. When they reached a configuration somewhere around that 1.5 AU mark, they are thought to have become locked into a specific orbital relationship, a 3.2 mean motion resonance. Meaning that for every 3 times Saturn completed an orbit around the sun, Jupiter completed exactly 2 orbits. This regular alignment created this powerful, resonant gravitational interaction between them.
And that pushed them outwards.
Instead of pulling them further inward, this specific resonance, interacting with the gas disk in a particular way, is thought to have reversed their migration. It caused both Jupiter and Saturn to migrate outward together, away from the sun, eventually settling near their current locations. Jupiter around 5.2 AU, Saturn around 9.5 AU.
That's an incredible journey. How long would all this have taken?
The whole process, the inward migration, the capture in resonance, and then the outward migration, or tack, is estimated to have occurred over a relatively short but cosmically significant period, maybe 3 to 6 million years in total, with the final outward migration possibly taking several 100,000 years of that.
Wow. That kind of planetary wandering must have had huge consequences for the rest of the solar system, right? What did this Grand Tack mean for us and the other planets?
The implications are, as you say, profound and really wide-ranging. It potentially shaped much of the solar system architecture we see today.
Like what, for instance?
Well, for one, the Grand Tack hypothesis offers a pretty compelling explanation for Mars's surprisingly small mass.
Ah, okay. How so?
As Jupiter migrated inward towards that 1.5 AU region, its immense gravity would have swept through the area where Mars was trying to form. It would have gravitationally scattered or absorbed many of the planetesimals in that region, effectively truncating the planet-forming disk at about 1.00 AU.
So it basically starved Mars of building material.
Exactly. It significantly limited the amount of stuff available for Mars to accrete, leaving it much smaller than Earth or Venus, which formed closer inside Jupiter's turnaround point.
And the asteroid belt, that sits right between Mars and Jupiter now. Jupiter must have plowed through that region twice.
Twice indeed, once on its way in and once on its way back out. And it wouldn't have been a gentle passage. Its gravity would have acted like a giant cosmic snowplow, or maybe more like a blender.
Stirring everything up.
Vigorously. It scattered asteroids both outward and inward across the solar system. The result is the asteroid belt we see today. A region with a surprisingly small total mass, much less than a single planet, and a population with a huge range of orbital inclinations and eccentricities. They're not all orbiting nicely in the same plane.
And it explains why the asteroids aren't all the same type.
Precisely. Jupiter's migration would have mixed things up, scattering objects that originally formed in the warmer inner solar system outwards and objects that formed in the colder outer regions inwards. So the asteroid belt is this cosmic melting pot containing material from across the early solar system, all thanks to Jupiter's journey.
So it's not just about shaping the things that are here, but maybe also explaining what isn't here. Like, we see lots of super-Earths around other stars, but we don't have any in our inner solar system. Could the Grand Tack explain that?
That's another fascinating implication, yes. Super-Earth's planets, typically larger than Earth but smaller than Neptune, seem incredibly common around other stars. Their absence here is a bit of a puzzle. The Grand Tack might offer a solution.
How? It's hypothesized that as Jupiter migrated inward, it could have gravitationally perturbed any early generation of super-Earths that might have formed in the inner solar system before Jupiter arrived. These perturbations could have driven them into unstable orbits, maybe causing them to collide, or even sending them spiraling into the young sun.
Wipe them out before they could establish themselves.
Possibly. Jupiter's inward march could have acted like a wrecking ball for any early inner planets.
And is there any physical evidence, maybe from meteorites, that points to this violent early period?
Yes, that's a really neat connection. The migration of these giant planets, particularly through the asteroid belt, would have significantly increased the average impact velocities between planetesimals. Things would have been hitting each other much harder than during simple, gentle accretion.
Okay.
This could explain the formation of some unique types of meteorites we find, called CB chondrites. These contain these distinctive metallic spherules that seem to have formed from molten droplets created in extremely high-speed impacts, maybe impacts faster than 18 kilometers per second. Wow, that's incredibly fast.
Much faster than standard accretion models predict. If these high-speed impacts are linked to the chaos stirred up by Jupiter's migration, it would place this event around 4.5 to 5 million years after the solar system started forming, giving us a potential timeline for the Grand Tack era.
That sounds like a pretty cohesive story, explaining a lot of different features. Yeah. But like any big, complex hypothesis, are there still ongoing debates or challenges to the Grand Tack? Is everyone convinced?
Oh, absolutely. It's definitely a field of active research and refinement. Science is always testing and questioning. While the Grand Tack successfully explains many things, scientists are constantly running new simulations, tweaking parameters, looking for potential problems.
Such as?
For instance, some later studies suggest that achieving and maintaining that specific 3.2 resonance between Jupiter and Saturn, which is crucial for reversing the migration in the original model, might actually be quite difficult to achieve robustly in a realistic fading solar nebula. It might be unstable.
So the outward tack might not work.
Well, other resonances, like a 2.1 resonance, might be more probable to form. But that resonance typically doesn't reverse migration on its own in the simplest models. Now, there are some specific nebula conditions and configurations where outward migration can be driven, even with a 2.1 resonance. But those scenarios often tend to overexcite the orbits of Jupiter and Saturn.
Meaning they end up too elliptical.
Exactly. They end up with much more elliptical or eccentric orbits in the simulations than the nearly circular orbits we actually observe for Jupiter and Saturn today. So getting the outward migration to happen and end up with the right final orbits is still a challenge.
So the core idea of giant planet migration seems solid, but the exact path, the tack, is still being fine-tuned.
That's a good way to put it. The evidence for some kind of significant migration seems increasingly strong, but the precise details of the journey, especially the exact resonance involved and how the outward migration stopped where it did, are still areas of intense research and debate within the scientific community.
Okay. Before we move on from Jupiter's origin, there's this common idea, or maybe misconception we should probably address. Given its huge size and the fact it's made mostly of hydrogen and helium just like the sun, people sometimes call Jupiter a failed star. Is there any truth to that?
Yes, the failed star idea. It's understandable why people think that, given the ingredients. Jupiter's made of essentially the same stuff as the sun. But the clarification is actually quite straightforward. Jupiter simply does not have enough mass. Not even close, really.
Not enough mass to do what? Ignite.
Exactly. To ignite and sustain nuclear fusion of hydrogen into helium in its core, which is the defining characteristic of a star, even the smallest, faintest stars, the red dwarfs, need about 75 to 80 times the mass of Jupiter to get that fusion going.
And brown dwarfs, aren't they sometimes called failed stars?
They are. Brown dwarfs occupy this interesting middle ground between giant planets and true stars. They're massive enough, typically starting around 13 times Jupiter's mass, to fuse deuterium, which is a heavy isotope of hydrogen, for a short period early in their lives. But they don't have enough mass to sustain the hydrogen to helium fusion that powers stars like our sun.
So where does Jupiter fit in?
Jupiter is well below that deuterium burning threshold. It has about 2.5 times the mass of all the other planets in our solar system combined, which sounds like a lot, but it's still only about 11,000th the mass of the sun. So while it's definitely the king of the planets, a true gas giant dominating our solar system, it's not a failed star. It's just a very, very successful planet.
A very successful and very large planet. Okay, so it formed, maybe took this incredible journey, but it hasn't just stayed the same since then, has it? It continues to evolve. And one surprising thing is that it's actually constantly shrinking.
That's right, it is. It's a fascinating aspect of Jupiter. It's still radiating away the immense heat left over from its formation billions of years ago. In fact, it actually radiates more heat into space than it receives from the sun.
Really? Where does that extra heat come from?
It comes from a process called the Kelvin-Helmholtz mechanism. Essentially, Jupiter's entire massive interior is still slowly, almost imperceptibly, contracting under its own immense gravity.
Contracting. Shrinking.
Yes. As it contracts, gravitational potential energy is converted into thermal energy, into heat. And that heat is then radiated away from its cloud tops into space. This ongoing process causes Jupiter to shrink by a tiny amount each year, maybe about 1 millimeter per year on average.
1 millimeter a year. Doesn't sound like much.
It doesn't day to day, but over the 4.5 billion years since it formed, it adds up. This slow contraction is the source of that excess heat it radiates.
So does that mean Jupiter was even bigger in the past, right after it formed?
Oh, significantly so. Right after its formation, Jupiter would have been much, much hotter, glowing perhaps dimly in the infrared, and probably about twice its current diameter.
Twice its current size. That's enormous.
Imagine that. A planet with a diameter roughly equivalent to where Saturn's main rings are today. But instead of rings, it's just this huge, hot, contracting gas ball. This ongoing contraction and cooling have played a major role in shaping its internal structure over billions of years, and also in driving its powerful atmospheric dynamics, the intense winds, the swirling storms we see today.
And speaking of that internal structure, our understanding of what's deep inside Jupiter has really changed too, hasn't it? I remember older ideas about its core were quite different. Some thought it might not even have one.
That's absolutely right. Before we had the kind of detailed data we have now, especially from the Juno mission, scientists had proposed sort of two main competing scenarios for Jupiter's deep interior.
What were they?
One idea was that Jupiter had a dense, compact, solid core at its very center, maybe made of rock and ice, something like a super-Earth buried deep inside. The other idea, especially popular if you favored the disk instability formation model, was that Jupiter might have formed through direct collapse from gas and dust, and thus might have no distinct core at all, just a progressively denser fluid interior all the way down.
So a solid core or no core? What did Juno find?
Juno's incredibly precise gravity field measurements have completely revolutionized our picture. The data revealed something quite different and actually much more complex and, well, messy. Jupiter appears to have what we now call a diffuse core, or sometimes a fuzzy core.
Diffuse, meaning not a solid ball.
Exactly. It doesn't seem to be a sharply defined solid object. Instead, it looks like a murky, partially dissolved region where the heavy elements, the rock and ice components, are mixed in with the metallic hydrogen that makes up most of Jupiter's deep interior. This mixed region extends out for a significant portion of the planet's radius, maybe somewhere between 30 and 50% of the way out from the center.
Wow, so a huge, slushy, mixed core region. How much heavy stuff is actually in there?
The estimates vary based on the models used to interpret the gravity data, but this diffuse core is thought to comprise heavy elements with a combined mass somewhere between 7 and maybe 25 times the mass of the entire Earth.
That's a pretty big range, 7 to 25 Earth masses. Why the uncertainty? And how could a core end up so diffuse, so spread out?
The uncertainty comes largely from how difficult it is to model the behavior of hydrogen and helium under the truly extreme pressures and temperatures deep inside Jupiter, millions of times Earth's atmospheric pressure. Small changes in how we assume those materials behave can lead to different core mass estimates. As for why it's diffuse, there are a couple of leading ideas, each painting a different picture of Jupiter's early life.
Okay, what are they?
One possibility is that this diffuse structure formed gradually during Jupiter's accretion phase itself. If Jupiter accumulated both solids, like planetesimals, and gases from the surrounding nebula simultaneously, rather than building a solid core first and then grabbing gas, it could have led to a mixed interior right from the start. The heavier elements would still tend to sink towards the center over time, but maybe never fully separated into a distinct, compact core.
So it was always kind of mixed.
That's one idea. The other, perhaps more dramatic hypothesis suggests that Jupiter initially did form a more compact, conventional core early on. But then, maybe a few million years after Jupiter's main formation, it suffered a massive catastrophic impact.
An impact with what?
With another large planetary embryo, perhaps something around 10 Earth masses itself. Such a giant collision could have been energetic enough to essentially shatter or disrupt that initial compact core, violently mixing its heavy element material throughout Jupiter's deeper mantle, creating the diffuse, spread-out structure we infer today.
Wow, a giant impact shaping Jupiter's core billions of years ago. That's quite a thought.
Either scenario, gradual mixing or a giant impact, points to a much more dynamic and perhaps violent formation and early evolution process for Jupiter than we might have previously imagined.
So the inside story is definitely more complex than just a simple core and envelope. What else have models revealed about the layers within Jupiter? And there's this really strange idea I've heard about helium rain. Does that actually happen?
Yes, the helium rain idea is one of the most fascinating predictions about the interiors of both Jupiter and Saturn. Our models of Jupiter's structure have definitely evolved from a simple two-layer picture to much more complex, potentially layered envelopes.
Okay, so what's the deal with helium rain?
Well, deep inside Jupiter, the pressures become so immense that hydrogen, which is normally a gas, transitions into a liquid metallic state. It behaves like a metal, conducting electricity. Now, at these incredible pressures and temperatures, theoretical models predict that helium, which is usually mixed uniformly with hydrogen in the upper atmosphere, might become immiscible in this metallic hydrogen.
Immiscible, like oil and water.
Exactly like oil and water. They don't want to mix. If this happens, the slightly denser helium would condense into droplets and essentially rain out of the surrounding metallic hydrogen, sinking down towards the deeper parts of the interior.
Wow. Do we see any evidence for this?
We actually see pretty strong evidence for it happening in Saturn. Data from the Cassini mission showed that Saturn's upper atmosphere is significantly depleted in helium compared to what we'd expect based on the Sun's composition or Jupiter's atmosphere. The best explanation is that helium has rained out into Saturn's deeper interior over billions of years.
And what effect does that have?
This helium rain is thought to be a major contributor to Saturn's surprisingly high thermal emission, why it radiates even more excess heat than Jupiter relative to the sunlight it receives. As the helium droplets sink, they release gravitational potential energy, adding to the planet's internal heat budget.
Does it happen in Jupiter too?
It's believed to play a role in Jupiter's internal thermal and compositional evolution as well, although perhaps to a lesser extent or starting later than in Saturn. Some models suggest that helium rain might have begun in Jupiter around 4 billion years after the planet formed, and it continues to subtly shape its internal structure and heat flow today.
But modeling all this must be incredibly difficult, right? Trying to figure out equations for how hydrogen and helium behave under millions of atmospheres of pressure.
It is exceptionally difficult, yes. There are still significant uncertainties in what physicists call the equations of state for these key components, hydrogen, helium, and even water under such extreme conditions.
Equation of state, meaning?
Think of it as the rulebook that describes exactly how a material behaves, its density, its pressure, its temperature, how compressible it is, especially when you push it to the absolute limits found inside a giant planet. Our current rule books for hydrogen and helium at Jovian pressures has error bars, uncertainties.
And those uncertainties affect our models of the core.
Directly. They affect our estimates of Jupiter's core mass, how fuzzy or spread out that core is, how heat is transported from the interior outwards. Additionally, another big uncertainty is our lack of precise knowledge about the exact depth of Jupiter's differential rotation. The fact that different latitudes and possibly different depths rotate at slightly different speeds How deep do those fast winds we see at the surface actually go?
Yeah.
That also adds uncertainty to our models of the internal structure. It's like trying to understand the inside of this incredibly complex, multi-layered spinning top without being able to truly see inside.
Okay, so the interior is still holding many secrets, but we can see the atmosphere, and we absolutely cannot talk about Jupiter's dynamic nature without discussing this great red spot. It's just iconic. What's the story behind this massive, enduring storm?
The Great Red Spot, or GRS, yeah, it's arguably Jupiter's most famous feature. It's this enduring, colossal anticyclone, essentially a giant high-pressure system spinning counterclockwise in Jupiter's southern hemisphere, specifically in the South Tropical Zone.
Anticyclone, high pressure.
Yeah.
So it's like a giant weather system on Earth, but way bigger and longer lasting.
Exactly. But on a scale that dwarfs any storm on Earth. What's truly remarkable about it is its incredible longevity. It seems to be unique among the various vortices we see in the atmospheres of the outer solar system planets. It's become the archetype of what atmospheric scientists sometimes call pancake vortices.
Pancake vortices. Why pancake?
Because their vertical thickness is much, much smaller than their horizontal dimensions. For the GRS, its horizontal scale, its width, is something like 50 times greater than its estimated vertical depth. This extreme aspect ratio likely contributes to its incredible stability and longevity. It's a vast, swirling, relatively thin pancake of a storm.
How long has it actually been around? Do we know when it started?
That's a great question, and the history is fascinating. The famous astronomer Giovanni Cassini first identified a distinctive, persistent oval spot on Jupiter, which he called the permanent spot, back in 1665. While we can't be 100% certain it's the exact same feature we see today, it's widely believed to be the earliest observation of the GRS.
1665. That's over 350 years ago.
Incredible, isn't it? It's been observed fairly continuously since the late 1800s. And when the Voyager probes flew by in 1979, they gave us those first truly detailed close-up images. They measured its diameter then at roughly 21,000 kilometers.
Which is almost twice the diameter of Earth.
Almost twice Earth's diameter fits inside this single storm. Just try to picture that scale. Earth could be swallowed whole by it.
Mind-boggling. What have we learned about its inner workings? What makes it tick? And crucially, how deep does this thing actually go? Is it just a surface feature?
Great questions. Data from various missions and telescopes, especially Hubble and Juno, have given us a lot more insight into its internal dynamics and structure. It's not just a simple swirl. It seems to have what's described as a hollow core, a region near the center with near zero relative vorticity, meaning the air isn't spinning much relative to the surrounding flow. This is surrounded by an outer region where the vorticity is nearly uniform, and then beyond that, there's an outer ring of cyclonic shear, where winds are shearing against the surrounding atmospheric bands, moving in the opposite direction.
Okay, so complex internal structure.
Yes, and observations also show that the absorption of blue light, which tells us something about the chemicals or aerosols present at different altitudes, is strongest near this calm, hollow core. And as for depth, Juno has been absolutely key. Before Juno, we didn't really know how deep storms like the GRS extended.
And what did Juno find?
Juno's microwave radiometer, which can peer deep below the visible cloud tops, revealed that the Great Red Spot extends incredibly deep into Jupiter's atmosphere. Its roots go down over 200 miles, or about 350 kilometers below the cloud tops we see.
350 kilometers deep. That's amazing.
It is. It reaches depths where sunlight doesn't penetrate to warm the atmosphere, implying its energy source must be coming from deeper within Jupiter. Other storms on Jupiter also extend significantly deep, typically 60 to 100 kilometers, showing that Jupiter's weather isn't just skin deep, it's a truly three-dimensional, churning, active environment.
So it's definitely not just a surface phenomenon, but a deeply rooted structure. How are its winds behaving over time? We hear reports that it's shrinking. Is it changing fundamentally?
Yes, the shrinking is real and well documented. Observations, particularly long-term monitoring by the Hubble Space Telescope using its Wide Field Camera 3 between 2009 and 2020, have meticulously mapped its complex horizontal wind patterns. The storm is definitely becoming more circular and smaller in overall area than it was in the past.
How much smaller?
In the late 19th century, observers estimated it was over 40,000 kilometers wide. By the time Voyager flew by in 1979, it was about 21,000 kilometers. And by 2014, Hubble measured it at just over 16,000 kilometers across, so it has shrunk significantly.
Is it weakening too?
Interestingly, while it's shrinking in area, the wind speeds at its outer edge seem to have actually increased slightly in recent years. So it's getting smaller, but perhaps spinning faster at the edges. We also see changes in its cloud appearance sometimes, like these features nicknamed flakes that were observed peeling off the edge in 2019. These seem to be produced near stagnation points in the flow areas where the winds might slow or eddy, and they can cause conspicuous changes in how the clouds look, but they might not necessarily affect the deeper atmospheric properties or the fundamental structure of the GRS itself. The long-term Hubble observations show no clear monotonic change in the mean wind shear over time, suggesting a remarkable internal stability despite these visible changes and the overall shrinking.
So is it truly infinite, as some people romantically say, or will it eventually just fade away? Feels like it's been there practically forever.
Despite its incredible longevity, entire nations, empires on Earth have risen and fallen during the time we've likely been observing the GRS. It is almost certainly not infinite. Given the observed shrinking trend over the last century or more, current predictions suggest it will continue to dissipate.
Any idea when?
Nobody knows precisely when, of course. Predicting the demise of a storm that's potentially over 350 years old is tricky. But based on the rate of shrinking, many scientists expect it to eventually end, perhaps becoming significantly smaller or less distinct within the next few decades or maybe centuries. It's a powerful testament to the dynamic, yet ultimately finite nature of even the most massive and seemingly permanent features in our solar system. Even cosmic giants evolve and change over time.
The Great Red Spot is such a powerful visual reminder of Jupiter's dynamic nature. But beyond its own spectacular features, Jupiter plays this incredibly significant, even foundational role in shaping our entire solar system, doesn't it? Its impact extends far, far beyond its own atmosphere.
It truly is a cosmic sculptor, yeah. Think back to Galilei again and his observations of Jupiter's 4 largest moons back in 1610.
Right, the Galilean moons.
Discovering those wasn't just about finding new stars out there. It was a fundamental revelation that directly challenged the centuries-old geocentric model, the idea that Earth was the fixed center of everything.
How so?
Galileo saw these 4 points of light clearly orbiting Jupiter, not Earth. It was undeniable proof that not everything in the heavens revolved around our planet. This provided crucial observational evidence supporting the idea that Earth itself could be a planet, orbiting a larger astronomical body, the Sun, just like Jupiter's moons orbited Jupiter.
Which was a radical, even dangerous idea back then.
Hugely radical, a heretical notion that went against established philosophical and religious dogma, but it fundamentally shifted our view of the universe and our place within it, paving the way for the acceptance of the heliocentric model. Jupiter, just by having moons, helped revolutionize human thought.
And it didn't just change our philosophical view, it physically shaped our cosmic neighborhood too, right? You mentioned the asteroid belt earlier, sitting there between Mars and Jupiter.
Exactly. Jupiter's powerful gravity acted like a kind of cosmic shepherd, or maybe a gravitational bully, depending on your perspective. As the solar system was forming, its immense gravitational influence strongly perturbed the region where the asteroid belt now lies.
What did it do?
It prevented the vast number of planetesimals, those small, rocky building blocks orbiting in that zone, from fully coalescing into a single, large planet. Jupiter's gravity constantly stirred them up, ejected many of them entirely, and generally made it impossible for them to accrete peacefully.
So instead of a 5th rocky planet, we got the asteroid belt.
Pretty much. The material was perturbed, scattered, its growth stunted. So today we have this vast belt filled with hundreds of thousands of leftover chunks of debris, a testament to Jupiter's dominant gravitational presence early on. It's like a fossil record of a planet that never quite managed to form, thanks to Jupiter.
Okay, this leads us naturally to that classic debate. Is Jupiter truly Earth's protector? Or is that just a comforting story we tell ourselves? It often gets called the solar system's vacuum cleaner because it gets hit so often.
That's a traditional view, and it's certainly intuitive. Given its immense gravity, it's by far the most massive object after the Sun, and its strategic location just outside the inner solar system, Jupiter definitely acts as a powerful gravitational attractor.
It takes a lot of hits for the team.
It does. Estimates suggest Jupiter experiences something like 200 times more impacts from asteroids and comets than Earth does. So, for a long time, the prevailing scientific view was that it primarily shielded the inner solar system, including Earth, by gravitationally sweeping up or deflecting many potentially hazardous objects that might otherwise come our way.
The cosmic vacuum cleaner.
Right. But there's a significant counter-argument, or at least a major nuance, to that picture. It's not quite so simple.
Okay, what's the other side of the story?
Well, some scientists argue that while Jupiter certainly intercepts many objects, basic probability and the physics of gravitational encounters mean it's just as likely to divert objects towards Earth as it is to divert them away from us.
How does that work? Like a gravitational slingshot?
Exactly. Think of a gravitational assist.
Yeah.
It can fling an object in almost any direction, depending on the precise angle and speed of the encounter. It doesn't just pull things in, it can redirect them, and sometimes that redirection sends them careening towards the inner solar system. Furthermore, Jupiter's gravity can actively stir up the asteroid belt itself through these things called orbital resonances. We mentioned the 3.2 resonance with Saturn earlier. Similar resonances exist between Jupiter and asteroids in the belt.
Like the Kirkwood gaps.
Precisely. When an asteroid's orbital period is a simple fraction of Jupiter's, say, it orbits twice for every one Jupiter orbit, a 2.1 resonance, or 3 times for every Jupiter orbit, 3.1. The repeated synchronized gravitational tugs from Jupiter happen at the same point in the asteroid's orbit, over and over.
And that pushes them out of those orbits.
It tends to pump energy into their orbits, making them more elliptical and unstable over long periods. These repeated nudges can eventually push asteroids out of the main belt and into orbits that cross the paths of the inner planets, including Earth. So Jupiter isn't just catching things, it's actively sending things our way from the asteroid belt, too.
Do we have any, geological proof of this stirring up actually leading to impacts on Earth in the past?
We do, actually. There's quite compelling evidence from the Ordovician period, around 470 million years ago. Geological studies suggest there was a major collision in the asteroid belt back then, possibly involving 2 large asteroids breaking apart.
Okay.
This collision seems to have happened in or near one of these unstable resonance zones with Jupiter. As a result, a huge amount of debris from this breakup, specifically a type of meteorite called L-chondrites, linked to the Gefion asteroid family, was nudged into Earth-crossing orbits.
And what happened on Earth?
Within a relatively short cosmic timescale, maybe a million years or so, Earth experienced a dramatic increase in meteorite impacts. We can see this clearly in the rock record. From that time, there's a massive spike, nearly 2 orders of magnitude increase, in the abundance of fossil meteorite fragments, like chromite grains, found in sedimentary rocks. And there's also a cluster of large impact craters dating to that same period.
So Jupiter's resonance basically aimed the debris from that asteroid collision right at us.
It seems highly likely that Jupiter's gravitational influence was key in channeling that specific debris shower towards the inner solar system, leading to what's sometimes called the Ordovician meteorite event. Without Jupiter's resonance stirring, that debris might have just stayed harmlessly in the belt.
That's fascinating and a very specific example. And I think I recall a story about a comet, too, that Jupiter definitely seemed to redirect towards us quite dramatically.
You're probably thinking of Comet Lexell back in 1770. It's a perfect, almost textbook illustration of Jupiter's complex dual role.
What happened with Comet Lexell?
This comet, discovered by Charles Messier, came streaking in from the outer solar system. It had a close encounter with Jupiter, and Jupiter's gravity completely changed its orbit, diverting it straight towards the inner solar system. It ended up making a remarkably close pass by Earth, only about 1.77 million miles away, which is just about 6 times the distance to the Moon. It was the closest known comet approach to Earth at that time.
So Jupiter definitely aimed that one at us.
It certainly seemed like it, but then comes the twist. 9 years later, in 1779, the comet swung back out near Jupiter again. And this time, Jupiter's gravity intervened again, but flung it in a different direction, completely ejecting it from the inner solar system, possibly out of the solar system altogether. It's never been reliably seen since.
Wow. Gave it a close shave and threw it out.
Exactly. It's a dramatic example of Jupiter's unpredictable gravitational sculpting. It can bring things close and it can throw them away.
So the conclusion on the whole Earth protector debate is, well, it's complicated. It's not just a simple shield.
Precisely. It's much more nuanced. While Jupiter undoubtedly intercepts a huge number of potentially hazardous objects, preventing them from reaching the inner solar system, its immense gravitational influence also has the undeniable potential to redirect other objects directly into our path, either through direct scattering or through resonant effects on the asteroid belt. So you could say Jupiter creates both good and bad conditions for life on Earth, gravitationally speaking. It's not a straightforward protector. It's a powerful, dynamic gravitational force that constantly reshapes trajectories, sometimes to our benefit, sometimes potentially to our peril. Its role is far more complex than just being a cosmic vacuum cleaner.
And we've actually seen impacts happening on Jupiter relatively recently, haven't we? It's not
Yeah.
just theory that it gets hit off and we've witnessed it.
That's one of the most exciting developments in planetary science in recent decades, actually witnessing these cosmic collisions in action. The most famous example, of course, was Comet Shoemaker-Levy 9, or SL9, which impacted Jupiter back in July
I
1994.
remember that. It was huge news.
It was a truly historic event. It was the first time scientists had ever directly observed an impact event between two solar system bodies as it happened. The comet itself had actually flown too close to Jupiter on a previous orbit and had been torn apart by Jupiter's immense tidal forces into about 21 distinct fragments.
Like a string of pearls, they called it.
Exactly. Hubble Space Telescope images showed this incredible string of pearls stretching out over 710,000 miles. That's 3 times the distance between the Earth and the Moon. And then, over several days in July 1994, these fragments, one after another, slammed into Jupiter's southern hemisphere.
What did it look like from Earth?
The impacts created these enormous, dark, bruise-like scars in Jupiter's clouds, some of them larger than the entire Earth. Ground-based infrared telescopes like NASA's Infrared Telescope Facility, IRTF, in Hawaii, observed them as incredibly bright spots, the fireballs and the resulting hot plumes rising high above the cloud tops. It was spectacular.
What did we actually learn scientifically from watching that happen in real time? How did it change our understanding of Jupiter or impacts?
The SL9 impacts were incredibly valuable for science. They gave us unprecedented insights into both impact physics and Jupiter's atmosphere. The collisions acted like giant depth charges, dredging up material from deep within Jupiter's atmosphere from below its visible ammonia clouds.
Stuff we normally can't see.
Exactly. Chemicals like ammonia itself and hydrogen cyanide, which are usually hidden deeper down, were lofted high up into Jupiter's stratosphere. These chemicals then acted as unique tracers, allowing scientists to track Jupiter's powerful high-altitude winds and study atmospheric mixing processes in a completely new way, complementing traditional cloud tracking.
So we could watch how Jupiter's upper atmosphere reacted and moved things around.
Precisely. And remarkably, changes in the abundance of hydrogen cyanide in Jupiter's stratosphere from those 1994 impacts are actually still detectable today, nearly 3 decades later. It gave us a way to probe the chemistry and dynamics of a layer of Jupiter's atmosphere that's usually very difficult to study. It significantly changed our understanding of Jupiter's atmospheric processes, its composition at depth, and also our models of how impacts work on giant planets throughout the solar system and beyond.
And SL9 wasn't the only one, right? There have been other impacts observed since then.
That's right. While SL9 was the most dramatic, there have been several smaller impact flashes observed since then, often first spotted by dedicated amateur astronomers who monitor Jupiter constantly. For example, in 2009, an Australian amateur astronomer named Anthony Wesley discovered a new dark scar on Jupiter, very similar in appearance to the SL9 impact sites, though smaller. Follow-up observations confirmed it was indeed the result of another impact, presumably from a smaller asteroid or comet nucleus, maybe a few hundred meters across. These ongoing observations reinforce the idea that Jupiter continues to be a frequent target for cosmic debris, allowing us to witness the solar system's ongoing evolution in real time.
It's amazing to think we can see that happening. Now, beyond these dramatic impacts, does Jupiter affect Earth's habitability and climate in more subtle, long-term ways? How does a giant planet so far away influence our home planet so fundamentally?
It's a really remarkable and often overlooked connection, but yes, Jupiter's influence extends even to Earth's long-term climate cycles. Its immense gravity doesn't just pull on comets and asteroids, it also gently but persistently tugs on Earth itself.
How does that affect us?
This constant gravitational interaction causes Earth's orbit around the Sun to vary slowly over very long timescales. Specifically, it affects the orbit's eccentricity. That's a measure of how circular or elliptical our orbit is.
And that changes our climate.
It does. This orbital variation is a key part of what scientists call the Milankovitch cycles, which are believed to be the main drivers of Earth's ice ages. When Earth's orbit is more eccentric or more elliptical, the amount of solar energy we receive varies more significantly throughout the year, and the total amount received annually can also change slightly. These long-term changes in orbital eccentricity, driven largely by gravitational tugs from Jupiter and Saturn, are strongly correlated with the coming and going of major ice ages on Earth, which seem to occur roughly every 100,000 years or so.
So Jupiter is essentially a kind of silent partner in pacing Earth's major climate shifts, like the ice ages.
In a way, yes. It's a major contributor to the gravitational beat that paces these cycles. Furthermore, Earth's tainted axis are apridy, which gives us seasons, and the slow wobble of that axis, known as precession, are also influenced by the gravitational pulls of the other planets, especially Jupiter.
And those are important for climate, too.
Absolutely crucial. The tilt gives us seasons, and precession changes which hemisphere is pointed towards the sun during different parts of the orbit over thousands of years. These factors are critical for things like allowing Earth to break out of an ice age. For example, an ice age often ends when the precession cycle causes northern hemisphere summers to occur when Earth is closest to the sun, maximizing the summer sunlight hitting the northern ice caps and allowing them to melt. This intricate dance wouldn't occur reliably without the gravitational influence of the giant planets, especially Jupiter, helping to stabilize and modulate these long-term cycles. So, Jupiter isn't just a distant giant. Its gravity is a fundamental part of the complex celestial mechanics that contribute to the long-term stability and conditions making Earth habitable over geological timescales.
Wow. Okay. We absolutely cannot do a deep dive on Jupiter without talking extensively about its moons. They're not just, little rocks orbiting a giant. They are incredibly diverse worlds, each with its own amazing story. It's like a miniature solar system in itself.
It truly is a system within a system, and their discovery by Galileo back in 1610, as we discussed, was just revolutionary for astronomy. These four largest ones, the Galilean moons, Io, Europa, Ganymede, and Callisto, are really substantial worlds in their own right.
Some are bigger than planets, right?
Ganymede is larger than the planet Mercury, and all four are among the largest moons in the entire solar system. What makes them even more fascinating, especially the inner three, is the intricate gravitational dance they perform.
You mean that strange cosmic rhythm they're locked into? The Laplace resonance?
That's exactly it. The inner three Galilean moons, Io, Europa, and Ganymede, are locked in what's called a Laplace resonance. It's this incredibly precise and stable orbital relationship.
How does it work again?
For every 4 times Io, the innermost one, orbits Jupiter, Europa orbits exactly twice, and Ganymede orbits exactly once. This perfect 4.2.1 ratio means they line up gravitationally in a very predictable pattern over and over again.
And that regular alignment has consequences.
Huge consequences. This resonance creates a constant gravitational tug-of-war. The neighboring moons repeatedly pull on each other at the same points in their orbits, preventing their orbits from becoming perfectly circular. They're forced into slightly elliptical shapes.
Okay, so they're not perfect circles. Why does that matter?
Because Jupiter's immense gravity then exerts powerful tidal forces on these moons, constantly trying to pull them back into a spherical shape and circularize their orbits. Since the resonance keeps forcing the orbits to be elliptical, the moons are constantly being stretched and squeezed by Jupiter's gravity as they move closer and farther away in their orbits.
Like kneading dough, almost.
That's a great analogy. This constant gravitational kneading generates immense internal friction within the moons. And that friction creates heat, a process known as tidal heating.
And that's what keeps them geologically active.
Precisely. It's this powerful tidal heating, driven by the Laplace resonance and Jupiter's gravity, that pumps enormous amounts of energy into the interiors of Io, Europa, and Ganymede, keeping them geologically active billions of years after they should have cooled down and become dead, frozen worlds. It completely changed our view of where geologic activity could happen in the solar system.
And Io is the most extreme example of this, right? A truly wild volcanic place.
Io is certainly the poster child for extreme tidal heating. Being the closest of the Galilean moons to Jupiter, it experiences by far the most intense tidal forces. It gets distorted, stretched, and squeezed like a celestial stress ball, generating tremendous internal heat.
And the result is volcanoes everywhere.
Hundreds of them. When the Voyager probes flew by in 1979, scientists were absolutely stunned to see hundreds of continuously erupting volcanoes spewing sulfurous plumes hundreds of kilometers high. They even saw vast lakes of molten sulfur on its surface. This discovery was revolutionary. It showed us that the outer solar system wasn't just a cold, dead, static place. Io's landscape is constantly being repaved by these eruptions, making it by far the most volcanically active body in the entire solar system. It's a world constantly turning itself inside out.
Incredible. And then moving outwards, we get to Europa. That's the one everyone talks about when they mention the search for life beyond Earth. What makes this icy moon so incredibly compelling?
Europa is compelling precisely because of what lies hidden beneath its icy shell. Its surface looks relatively smooth, but it's crisscrossed by these long linear cracks and ridges hinting at activity below. And beneath that icy crust, which might be maybe 10 to 15 kilometers thick, we have very strong evidence for a vast global ocean of liquid salt water.
An ocean under the ice. How big?
Estimates suggest this subsurface ocean could contain more than twice the volume of all of Earth's oceans combined.
Wow. And it stays liquid because of that tidal heating.
Exactly. Thanks to the continuous tidal heating from Jupiter, Europa's deep interior is kept balmy enough, relatively speaking, to maintain this enormous amount of liquid water just beneath the ice shell. Furthermore, there's evidence suggesting potential hydrothermal activity on Europa's seafloor, where the ocean meets the rocky mantle below. These could be like the hydrothermal vents we see on Earth's ocean floors.
Which on Earth support entire ecosystems.
Precisely. On Earth, those vents provide chemical energy that supports life forms completely independent of sunlight. So the combination of liquid water, potential energy sources from tidal heating and maybe hydrothermal vents, and the expected presence of necessary chemical ingredients makes Europa a prime target, arguably one of the top targets in our solar system, for exploring planetary habitability and searching for signs of extraterrestrial life. It's why missions like Europa Clipper are so exciting.
Definitely. Okay, next out is Ganymede. You mentioned it's huge, even bigger than Mercury. What else makes Ganymede special?
Ganymede is indeed a giant, not only the largest moon in the solar system, but bigger than Mercury and the dwarf planet Pluto. It's a truly differentiated world with likely an iron core, a rocky mantle, and perhaps even its own subsurface ocean sandwiched between layers of ice. But what makes Ganymede truly unique among all moons in the solar system is that it possesses its own internally generated magnetic field.
A moon with its own magnetic field.
How? It's the only moon known to have one. It strongly suggests that Ganymede has a convecting liquid metallic core, likely molten iron or an iron-sulfur mixture, deep inside, generate a magnetic field through a dynamo process similar to how Earth generates its field. This discovery by the Galileo orbiter was another major surprise.
Amazing. And then the last of the big four is Callisto, the outermost one. What's its story? Is it also active?
Callisto is interesting because it's quite different from the inner three. It's still a very large moon, about the size of Mercury, but it orbits much further out from Jupiter. This means it's not part of the Laplace resonance, and it experiences much, much weaker tidal heating.
So it's less geologically active.
Much less. Its surface is ancient and incredibly heavily cratered, indicating far less resurfacing activity compared to the others. It's considered more of a classic icy moon, possibly with a subsurface ocean, but without the intense geological dynamism of Io, Europa, or even Ganymede. However, its location has a key advantage for potential future exploration.
Which is?
Callisto orbits outside Jupiter's main, most intense radiation belts. This makes it a significantly safer and thus potentially more accessible target for long-term robotic missions or even human proximity in the very distant future compared to the incredibly harsh radiation environments around the inner three moons.
And what would Jupiter look like from Callisto?
If you were standing on Callisto's icy surface, Jupiter would absolutely dominate the sky. It would appear roughly 10 times larger in diameter than our own moon appears from Earth. It would be a truly awe-inspiring sight.
Incredible. And those are just the big four, the Galilean moons, the Galileo saw.
Yeah.
But Jupiter has a lot more moons, right? Like dozens and dozens more.
Oh, yes. It's a truly vast retinue. As of now, Jupiter has at least 97 confirmed moons, and the number keeps ticking up as we find smaller ones. It really is a mini solar system presided over by the giant planet itself.
How are all those other moons categorized? Are they similar to the big four?
Not really. They're broadly classified into different groups. There are the inner moons, sometimes called the Amalthea group, which are relatively small, irregularly shaped bodies orbiting very close to Jupiter, inside Io's orbit, likely embedded within Jupiter's faint ring system.
Okay. And then further out.
Then much further out, beyond Callisto, you have the irregular moons. These are typically much smaller, follow highly inclined and eccentric orbits, and are often grouped together based on their orbital characteristics, suggesting they might be fragments of larger bodies that were captured by Jupiter's gravity long ago.
Captured asteroids or comets.
That's the leading theory for most of them. They're clustered into several named groups, like the Himalaya group, which orbit in a prograde direction, same as Jupiter's rotation, and then several large groups orbiting in a retrograde direction, opposite to Jupiter's rotation, such as the Carme, Ananke, and Pasiphae groups. There are also smaller groups like Carpo, Each of these groups and the individual moons within them tells us something about the history of captures and collisions in the outer solar system, adding to the incredible diversity and complexity of the whole Jovian system.
It's just staggering. The sheer scale of Jupiter, its system. It's honestly hard to properly wrap your head around it, isn't it? It's one thing to see the pictures or read the numbers, but to truly grasp its size or imagine the hazards of actually being near it, that seems almost impossible for our brains.
You've hit on a really key point there about human perception of scale. Our brains evolved here on Earth, and they're just not intuitively equipped to grasp dimensions as immense as Jupiter's or the distances involved. You mentioned the Great Red Spot being larger than Earth. That alone is hard to truly internalize.
Yeah, it just becomes a number.
Exactly. It's like trying to perceive the true scale of, say, Yosemite's sheer granite cliffs from the valley floor. You see them, but it's hard to truly register how massive they are until maybe you spot impossibly tiny climbers on the face, or realize that what looks like fuzzy stubble near the top is actually a forest of 100-foot-tall pine trees. Our brains struggle to interpret such immense distances and sizes without familiar reference points.
I've heard even in VR, planets can look flat unless you tweak the settings.
That's right. Even in detailed virtual reality simulations, if the stereoscopy, or the simulated distance between your virtual eyes, isn't adjusted correctly for the vast distances, planets can look like flat 2D disks hanging in space rather than massive three-dimensional spheres. To actually perceive Earth as a 3D sphere from the orbit of the International Space Station, your eyes would need to be separated by about 500 meters. So yeah, comprehending Jupiter's true mind-bending scale is a constant perceptual challenge.
And I imagine getting close to Jupiter in person, if we could, would come with some pretty significant dangers beyond just being overwhelmed by its size. We're talking about incredibly intense radiation belts, aren't we?
Absolutely. Lethal levels of radiation, yes. Jupiter possesses by far the most intense radiation belts in our entire solar system. They dwarf Earth's Van Allen belts in both size and intensity.
What creates them?
They're created by Jupiter's incredibly powerful magnetic field, the strongest of any planet, which traps energetic charged particles, mostly electrons and ions, primarily originating from the volcanic moon Io and also from the solar wind. Jupiter's rapid rotation then accelerates these trapped particles to relativistic speeds near the speed of light, creating these belts of incredibly high-energy radiation.
How dangerous are we talking, especially near those inner moons?
We're talking extremely dangerous. Particularly around the orbits of the inner Galilean moons Io, Europa, and Ganymede, the radiation levels are so intense they would be rapidly fatal to an unshielded astronaut, and they pose a huge challenge even for heavily shielded robotic spacecraft. Any future human missions venturing into that region would require extremely heavy shielding, potentially meters-thick layers of dense materials like lead or perhaps water, just to protect the crew from the constant bombardment of deadly radiation.
So visiting Europa or Ganymede directly is a major engineering challenge.
A massive one. That's why Callisto, orbiting much further out, beyond the most intense points of the radiation belts, is often considered a much safer, more feasible potential destination for long-duration robotic presence, or even potential human exploration bases in the very distant future. Even there, significant shielding would still be required, but it's considerably less hostile than the inner system.
Okay, so for the foreseeable future, it's really unmanned robotic exploration that's leading the way in unraveling Jupiter's secrets. And there's already a pretty rich legacy of discovery built up over decades of missions, isn't there?
Indeed, robotic explorers have been our eyes, ears, and even noses in the Jovian system for decades now, each mission building on the last. The very first glimpses came from the Pioneer 10 and 11 flybys back in the early 1970s. They gave us our first close-up images and fundamental measurements of Jupiter's intense magnetic field and radiation belts, confirming they were far stronger than expected.
And then Voyager came along.
Then came the iconic Voyager 1 and 2 probes, which flew through the Jupiter system in 1979. They provided those absolutely stunning, detailed images of Jupiter's swirling atmosphere, the Great Red Spot, and crucially, the Galilean moons. Voyager's discoveries, Io's shocking volcanism, Europa's smooth, icy, potentially ocean-bearing surface, Ganymede's size fundamentally changed our understanding of the outer solar system.
After the flybys, we sent an orbiter, right? Galileo.
Yes, the Galileo mission was truly groundbreaking. Launched in 1989, it arrived at Jupiter in 1995 and became the first spacecraft ever to orbit the giant planet. It spent 8 highly successful years studying Jupiter, its moons, and its magnetosphere in unprecedented detail, despite a problem with its main antenna deploying fully.
Didn't Galileo also send a probe into Jupiter's atmosphere?
It did. That was a major highlight. Galileo carried an atmospheric probe that detached from the main orbiter and plunged directly into Jupiter's turbulent clouds. It collected invaluable data on temperature, pressure, chemical composition, and wind speeds for a remarkable 57.6 minutes as it descended, before it was ultimately crushed and vaporized by the immense pressure and heat deep within the atmosphere. It gave us our only direct sampling so far of Jupiter's atmospheric layers.
Wow. What happened to the main Galileo orbiter?
After completing its extended mission, the Galileo orbiter itself was deliberately commanded to plunge into Jupiter's atmosphere in September 2003. This was done specifically to ensure there was absolutely no chance of it accidentally crashing onto Europa in the future and potentially contaminating that moon's potential subsurface ocean with microbes from Earth. It was a responsible end to a fantastic mission, prioritizing planetary protection.
A necessary precaution. And now, the most recent major mission is Juno, which is still operating. How has Juno taken our understanding to the next level? What's its unique contribution?
Juno has truly been another game changer, leveraging new technology to probe Jupiter in ways Galileo couldn't. Launched in 2011 and orbiting Jupiter since July 2016, Juno's primary mission is to understand Jupiter's origin, internal structure, deep atmosphere, and magnetosphere. Its highly elliptical, polar orbit takes it incredibly close over Jupiter's poles, much closer than Galileo got, allowing it to map Jupiter's powerful gravity and magnetic fields with unprecedented precision.
And that's how we learned about the diffuse core.
Exactly. That detailed gravity mapping is what revealed the fuzzy, diffuse nature of Jupiter's core. Juno is also giving us our first real 3D views of Jupiter's atmosphere. Its microwave radiometer instrument peers deep beneath the visible cloud tops, hundreds of kilometers down, revealing the structure and dynamics of Jupiter's famous cloud bands, the zones and belts, and showing that they extend far deeper than many scientists had expected.
What else has it found in the atmosphere?
Juno has provided stunning close-up images of Jupiter's poles, revealing complex arrangements of huge, persistent polar cyclones, unlike anything seen elsewhere. And it helped solve a long-standing puzzle about missing ammonia in certain parts of Jupiter's atmosphere. Juno data led scientists to identify features they nicknamed mush balls.
Mush balls, like slushy hailstones.
Essentially, yes. They seem to be large hailstones made of a mixture of ammonia and water ice, forming high up in Jupiter's powerful thunderstorms. These mush balls are thought to efficiently capture ammonia gas as they fall, carrying it down to much deeper, unseen layers of the atmosphere before they melt or sublimate. This explains why microwave observations sometimes see less ammonia than expected at certain altitudes. It's been temporarily locked up in these falling mush balls, a really elegant solution to a long-standing mystery.
That's clever. Now, beyond just studying Jupiter itself, haven't we also used Jupiter's immense gravity as a kind of cosmic slingshot to send missions elsewhere in the solar system?
Absolutely. Jupiter's gravity is so immense, it's incredibly useful for what we call gravity assists. It's become a standard technique in mission planning. NASA and other space agencies have repeatedly leveraged Jupiter's gravity to accelerate spacecraft and or redirect their trajectories, saving huge amounts of fuel and travel time.
Which missions have done this?
Oh, quite a few famous ones. The Cassini mission, which spent 13 amazing years orbiting Saturn, used a Jupiter flyby for a crucial speed boost to get it out to Saturn efficiently. The New Horizons mission, which gave us our first close-up look at Pluto and is now exploring the Kuiper Belt, got a massive velocity kick from Jupiter. Even the Ulysses mission, which was designed to study the Sun's polar regions, used the Jupiter flyby to fling it out of the plane of the solar system into a unique polar orbit around the Sun. Jupiter essentially acts as a free cosmic accelerator for exploring the outer reaches.
It's a handy neighbor to have, gravitationally speaking. Okay, looking ahead now, what about future missions? Where are we headed next in our exploration of the king of the solar system and its realm, especially concerning that tantalizing search for life?
The future is incredibly exciting, particularly with the continued focus on Jupiter's potentially habitable ocean moons. The flagship mission leading the charge right now is NASA's Europa Clipper, which, as you noted, successfully launched on October 14th, 2024.
What's Europa Clipper going to do? Will it land?
Clipper won't land, and it won't orbit Europa directly. The radiation environment is just too harsh for a long-duration orbiter with current technology. Instead, it will orbit Jupiter itself, but on a cleverly designed trajectory that allows it to make approximately 50 close, targeted flybys of Europa over several years. Some of these flybys will bring it incredibly close, maybe as low as 25 kilometers or about 16 miles above Europa's icy surface.
Wow, skimming the ice. What we'll look for.
It carries a sophisticated suite of 9 scientific instruments designed to investigate Europa's habitability. It will use radar to probe the thickness of the ice shell and search for subsurface lakes or even the ocean itself. Spectrometers will analyze the composition of the surface ice and any plumes that might be erupting. Magnetometers will help characterize the ocean's depth and salinity by measuring how Europa interacts with Jupiter's magnetic field. Cameras will provide high-resolution images of the surface geology. The goal is to gather comprehensive data to determine if Europa indeed possesses the necessary conditions, liquid water, chemistry, and energy that could potentially support life as we know it.
It's not looking for life directly, but for the conditions for life.
Exactly. It's characterizing the habitability, paving the way for potential future missions that might be designed to land and search for biosignatures directly.
And there was that really neat public engagement initiative connected with Europa Clipper, wasn't there? The message in a bottle.
Yes, that was a wonderful initiative. NASA ran the Message in a Bottle campaign, inviting people all over the world to sign their names online. Over 2.6 million names were collected and electronically stenciled onto a tiny microchip using an electron beam.
Wow, and where is that chip now?
That microchip, carrying all those names, is affixed to a commemorative metal plate mounted on the side of the Europa Clipper spacecraft. The plate also features graphics related to the mission and, most touchingly, an original poem titled In Praise of Mystery, a poem for Europa, written by the U.S. poet laureate Ada Limon specifically for the mission. It's a beautiful way to connect humanity's artistic and scientific impulses, uniting art and science and allowing millions of people to feel a personal connection to this incredible journey of exploration to the Jupiter system. It's a powerful symbol of our shared, collective curiosity about the universe and our place in it.
That really is fantastic. It's not just about the complex hardware and the hard science data, but also about that human element, that sense of shared adventure, even if we're sending robotic proxies out there for now. And thinking about those future robotic missions, especially potential landers on these challenging icy moons, what kind of cutting-edge technology are we developing to make those possible?
That's a critical area. Landing and operating on a distant, hazardous, and largely unknown world like Europa requires incredible levels of autonomy. Communication delays between Earth and Jupiter can be an hour or more round trip, making real-time joystick control impossible. The spacecraft has to be smart enough to handle situations on its own.
So we need smarter robots.
Essentially, yes. NASA and other institutions are actively developing advanced autonomous software systems specifically for these kinds of challenging missions. There are projects like OWLAT, the Ocean World Lander Autonomy Testbed, and Ocean Waters, which stands for Ocean World's Autonomy Testbed for Exploration Research and Simulation. These programs are using cutting-edge techniques from artificial intelligence, including machine learning, automated reasoning, and even generative AI.
How will AI help a lander on Europa?
This advanced software is being designed to give future landers and rovers the ability to do several key things autonomously. First, enhanced fault recognition and recovery, allowing the probe to diagnose problems with its systems and attempt to fix them or work around them without waiting for instructions from Earth. Second, adaptive science planning, enabling the probe to recognize scientifically interesting features it encounters unexpectedly and adjust its planned activities to investigate them further. And third, sophisticated terrain adaptation and navigation, allowing a rover, for instance, to analyze the complex, potentially hazardous, icy terrain around it and figure out the safest path forward, all on its own. These capabilities will be crucial for exploring these dynamic and unpredictable environments effectively.
Building robots that can think for themselves in other worlds. That's
Yeah.
amazing. Now, looking even further out, beyond Jupiter's system, is there a push for more missions to the really distant planets? Yeah. The ice giants.
Absolutely. There's a very strong and growing consensus within the planetary science community that a dedicated flagship mission to one of the ice giants, Uranus or Neptune, should be a top priority for the coming decades.
Why the focus on them now?
Because these planets represent a fundamentally different class of giant planet compared to Jupiter and Saturn, and they remain largely unexplored. Our only close-up data comes from the brief Voyager 2 flybys back in the 1986 for Uranus and 1989 for Neptune. Those flybys revolutionized our view but raised far more questions than they answered.
What kind of questions?
We still don't really understand their internal structures, why the magnetic fields are so bizarrely tilted and offset, the detailed composition of their atmospheres, which seem different from Jupiter's and Saturn's, or how their systems of rings and moons formed and evolved. A dedicated orbiter mission, similar to Galileo at Jupiter or Cassini at Saturn, would provide invaluable, transformative data to understand these enigmatic worlds and complete our reconnaissance of the major planet types in our own solar system. It's seen as a critical next step in planetary exploration.
So the drive to explore continues outwards.
It does. All these missions, past, present, and future, from Jupiter to Europa to the ice giants, really reflect this fundamental, innate human drive to understand our universe, to figure out how things work on the grandest scales, and to answer that profound question, are we alone?
What an incredible journey we've taken today, just talking about Jupiter. From its, well, possibly violent and dynamic birth, maybe doing that grand tack across the entire early solar system,
A wild ride if it happened.
to its ongoing powerful influence as a true cosmic sculptor, shaping everything around it. Jupiter really is the king of our solar system, no question.
It sets the rules in many ways.
Yeah. We've seen how it potentially reshaped planetary orbits, how it influences Earth's long-term climate, and how it continues to be this amazing frontier for exploration, especially with the tantalizing prospect of finding life, or at least habitable conditions, on its icy moons.
It's just a constant source of surprises and new questions.
It really is. It's a perfect testament, I think, to the fact that there's always more to learn out there, and that human curiosity, when we pursue it, can lead us to the most incredible discoveries and insights.
And here's a final thought to leave you with. Consider this. If a single storm system on Jupiter, the Great Red Spot, can persist for centuries, outlasting entire human civilizations, what does that really tell us about our perception of time, about the nature of change and permanence on cosmic scales?
It makes you feel small.
And perhaps, more hopefully, what secrets might those icy moons, Europa especially, still hold deep beneath their frozen shells? Could answers about life beyond Earth be patiently waiting there, just waiting for us, or our robotic explorers to finally discover them?
Provocative questions indeed. Something to think about.
Definitely.
Thanks for listening to All in All.